Hello again. This is the second part of the video series about the first law of thermodynamics. And as already said at the end of the last video, in this video, the first law of thermodynamics will be further explained or illustrated with examples utilizing the concept of the ideal gas. So in physical chemistry textbooks, often the study or the explanation of the first law of thermodynamics is often done with ideal gases first, and also so do I. So study often done, or explanation often done with ideal gas concept. So I don't know if one has not heard about the ideal gas. Some things have to be known, or some relationships have to be known to follow the content of this video. The first concept is that the pressure times the volume equals the number of moles times ideal gas constant times temperature. So this here is the pressure, then the volume of an ideal gas, and just very briefly, this is the amount of substance, and this is the temperature in kelvins. This is the number of moles. And yes, ideal gas, just to describe a bit, there are no interactions between the gas molecules, the gas atoms here actually. Ideal gas. Monoatomic, I forgot. Everything that I say about ideal gas is for the monoatomic ideal gas. So there are no gas molecules, just atoms. And the interaction, there is no interaction between the atoms, and the atoms in itself, they have no volume. And besides this, the CV, which is the volume heat capacity, so this means it denotes the energy that is required to heat up the sample such that its temperature rises up 1 Kelvin. So then CV equals 3/2 times the ideal gas constant times the number of moles. And there must also be a change in inner energy, or a function U, that describes the change of inner energy. And delta U equals to P, the integral from temperature 1 to temperature 2, CV dt. And since CV does not depend on the temperature, this equals to P 3/2 times ideal gas constant times amount of substance T2 minus T1 equals 3/2 Rn delta T. So as already explained in the last video, there must be a function that allows us to calculate delta U. It's U equals 3/2 Rn T, and this expression here equals U2 minus U1. So also for the ideal gas, the total energy is a state function, and the differential change, or du, is an exact differential. So did I forget anything we need for further explanation? I don't think so. If so, I will cover it when I will find it out. But I think now this is everything we need for giving some examples of the first law of thermodynamics by utilizing the ideal gas concept. So next I would like to illustrate the concept of work for an ideal gas. So up to now we had no function that gives an expression for dW or W, but we can do it now for the ideal gas. So first consider that you have a box, or let's say a cylinder, and in the cylinder there is an ideal gas with a certain pressure, and there is a lid which cannot slide down because it is fixed, and on top of this lid there is a mass, and because of this mass there is a downward force on the lid, so F equals m times gravitational constant, and this would be initial state or state number 1. And generally one can say that there is an external pressure acting on the gas inside. And if I remove these holders here, then the lid will slide down until there is an equilibrium, or the gas, let's say, cannot be compressed anymore by the weight here. Sorry, draws a different color. So afterwards there is force equilibrium. So for completeness there is external pressure, and this would be state number 2. Now we know that the work can be calculated with the height difference. So it is minus the force that the minus, forget about the minus right now, I'll explain this later. We would like to find an expression for the work. So the work is equal to force times distance. So the force is mass times gravitational constants. The difference is the height difference, h2 minus h1. So here it would be h2, and here the height would be h1. And now if we multiply and divide with the area of this lid here, this would mean that we change essentially nothing mathematically, but we can introduce a different notation, because this here we can identify as the external pressure that is acting on the lid, and this is volume 2 minus volume 1. So volume 1 here is the initial volume, and here we have volume 2 after compression, and this can also be written as P external times delta V. And because this is now convention, we say, because the gas is finally compressed, work has been done on the system, on the gas, and therefore the value of the performed work is positive. But since h2 is smaller than h1, this expression here is negative, and therefore we had to add a negative sign here. Negative, negative, negative. So now we have found an expression for work when dealing with the ideal gas, and as explained in the last lecture, the work is not an exact differential. Therefore, we write here this curly d dw equals, I write down the differential form, it's minus p minus the external pressure times differential change in volume. And in the PV diagram, this change looks like this. So we have here the pressure, we have here the volume, and during the whole process, the pressure acting on the lid is the constant, namely P external, and we perform a compression. So here it's V1, here it is V2, and the area under this curve describes the work done to the ideal gas by the external force. An interesting concept here is the reversible process for work. So here the external pressure is constant, but in a mind experiment one can think that the external pressure always equals the internal pressure, in this case during compression, but such a process would be infinitesimally slow, therefore in reality it doesn't exist. But in a thought experiment we can use this for explaining concepts. So let's say the reversible process, and I forgot, we are dealing with the condition that the temperature is constant. Temperature constant. For such a process, it means that P external equals P always at any time. This means we can use now a concept from the first slide, namely we can use the ideal gas law here. So if P is the pressure inside the cylinder, we just can rearrange and get an expression for the reversible process at constant temperature. So dW, let's write this again, would be P dV, because P external is now P in the reversible process. And as we have stated on the slide before, not on the initial slide in this video, not slide before, that P can be expressed as nRT divided by V. And this means now that if we plug in here, it's minus nRT divided by V dV. And if we calculate the total work, this means we can now integrate. Let's say we start at volume 1, end up at volume 2, nRT V dV. And because we are our assumption is that the temperature is constant, we can move n r and t in front of the integral. And we write on the integral again, and this can be evaluated to be minus nRT times the natural logarithm of the ratio V2 over V1, and let's rewrite this again by using the rules of logarithms. It's V1 over V2. If we compare this with this process here, then let's say we also start at V1 and then we compress if we start at V1 and end up at V2 for the reversible process at a constant temperature, we get a different curve that would go like this, because in this case here the external pressure is much higher than the internal pressure. Therefore at V1 we start at a lower point for the pressure, and the area under the curve is also lower than for the process with the constant external pressure. As a matter of fact, this is the minimum work required at constant temperature for compressing the gas. For expanding the gas, it would be the maximum work that one gets out of the gas mixture if one would move from state 2 to state 1. But here the take-home message is that if you have a reversible process which is would be infinitesimally slow and therefore in reality doesn't exist, but conceptually this would mean for such a process would require the least or the minimum amount of work for compressing the ideal gas, because the curve here or the integral under the curve is much smaller than for the process with a constant external pressure. So now what we have now found or got some training with the concept of work for the ideal gas, which is useful for when studying the first law of thermodynamics with the ideal gas concept, and we also derived an expression for the ideal gas when the external pressure is constant, or a general term for the let's say work when using the concept of an ideal gas. And what I forgot to say, in our examples we are just dealing with the concept of volume work. This is a very particular case I forgot to mention, but very useful when explaining thermodynamic properties. So next I would like to introduce some nomenclature. Some nomenclature we already had, but just some terms now that are quite often used in chemical thermodynamics. So first it's let's consider the isothermal process. So process, for sake of completeness, let's say you have some property. This property depends on variables, and a process would be changing the variables. Let's put it like this. And if temperature is a variable, then and for an isothermal process, the temperature is constant. And for an isobaric, process, the pressure is constant. For an isochoric process, the volume is constant. And for an adiabatic process, big Q equals 0. This means that also differential change of, sorry, this also means dq is 0. And this means that no heat is exchanged with the surrounding. Let's say you have an ideal gas, it is in a cylinder, and then the walls prevent heat being exchanged between the ideal gas and the surrounding. Or otherwise you cannot heat up, or stated differently, you cannot heat up or cool down the gas. So no heat is exchanged with the surrounding. Sorry, my handwriting is already late. Yeah, then first would be, let's talk a bit about the Isobaric process. So pretty much we already had it in the last slide, but let's do it again for sake of completeness and for practicing. Yeah, I have a PV diagram, pressure, volume, and let's say you have volume 1 and volume 2. So now we expand the gas and the pressure is constant. Here this would be the area underneath the pressure function. Then for such a process, the work is minus the integral of P dV, and it's minus P delta V equals minus P V2 minus V1. And in our case, if we go in this direction here, we expand the gas, then V2 minus V1 is positive, then the work is negative because the gas has performed work in its environment in this terminology. Or per convention in such a case, W has to be smaller than 0. And this means that with what we already know about the first law of thermodynamics, that delta U equals Q plus W, it is Q minus P delta V. And P in this case is always P external. And because we know delta U equals the integral from T1 to T2 CV dt, and for the ideal gas CV, or the volume heat capacity, it's 3/2 R as the ideal gas constant times amount of substance, which is the number of moles, times delta T, and delta T is T2 minus T1. So this also means that we now can calculate Q. It is 3/2 Rn delta T plus P delta V. So now we have also found an expression for the transferred heat for an isobaric process in general. And note that if I set Q equals to B0, then if one rearranges everything, then one finds that delta T equals minus P delta V 3/2 RTN. And for this particular example here, this means that this term here is lower than 0 because the pressure is bigger than 0, delta V is bigger than 0, RT and N are also bigger than 0, then the whole expression is lower than 0. So this means that in this case an ideal gas cools down when expanded. So because the ideal gas performed work on its surrounding, therefore we had to pay a price which is a decrease in temperature. So next thing would be we study an adiabatic process that is reversible. So adiabatic and reversible. So again, we know our expression for work. So integral minus p dv being evaluated between v1 and v2, and because we are dealing with the reversible case here, we can replace again p equals to b nRT divided by v. This means minus the integral y1 over y2 nRT divided by v dv. And adiabatic means that exchange heat is 0. So again, our delta U, the change in total energy, is 3/2 R1 of substance times delta T. And then the goal of this example here is to show that also for the adiabatic and reversible case, there is a temperature change when expanding or compressing the gas. So for this purpose, let's write this expression here and the expression for work in differential form. So first of all, we know delta Q again is Q plus W, and because Q is 0, it's only W. And a differential form, this means it's du, and now we can also write here, or let's write the word channel form, don't avoid any confusion. Or maybe it's better like this, yeah, more correct. Here there's also not a Latin D, because if this is a exact differential, this also must be an exact differential. However, let's now write this in differential form. du equals to be 3/2 Rn dt, and this equals to be minus nRT over v dv. So now there are some redundant terms like ideal gas constant, amount of substance, and if we rearrange this here, we end up with the following expression. It's 3/2 dt divided by t equals minus dv divided by d. And if we integrate now on both sides, meaning that here we draw the integrals are from t1 to t2, and here from v1 to v2, this leads to the following expression. Here again we have 3/2. It's negative, the natural logarithm of the ratio t2 over t1. This is minus the natural logarithm of the ratio v2 over v1, and by applying the rules for the calculation rules for logarithms, this evaluates to be v1 over v2, and the pre-sign here changes from negative to positive. And also by using the rules of logarithms here, this prefactor could also written as an exponent of this ratio here, and then eventually one ends up with the expression t2 over t1 to the power of 3/2 equals V1 over V2. So now in our particular case, let's say we expanded the gas, meaning that V2 is much bigger than V1. So this term here must be lower than 0. This also means that T over T1 must be lower than 0, but this means that T1 is bigger than T2. So let's write this down. So if V2 is bigger than V1, it follows that T1 is bigger than T2. Or in other words, if one expands the gas, the ideal gas in an adiabatic and reversible process, then the gas cools down, as it was the case for the isobaric example. So if no heat exchange is allowed, the gas has to pay a price, so to say, for the volume expansion. This is useful for being remembered when studying further examples. So, next case, what is already covered somehow. We have covered the isobaric process. Then adiabatic process is also somehow covered. Reversible process we have explained in the foils before, but now from these three courses, isobaric and adiabatic process are covered. So next next process I would like to explain is the isochoric one. So an isochoric process for the ideal gas, that means that delta V, so the change in volume is 0. Means also that differential change in volume is 0. In the PV diagram, this looks like this. Here it's the volume, it's the pressure, and in such a process we go along a vertical line. This already means that the work is 0. So the work is 0 because we have found the expression for work. It's the infinitesimal change of work is PdV. dV is 0, so total work is also 0. But this, on the other hand, means if we remember our equation that du equals dq plus dw, since dw is 0, it is only dq. And the change in inner energy can be written as follows: it's 3/2 R n T final, or T2 minus initial, and this also equals the exchanged heat. Next thing, then we also have covered the isochoric process, and next thing would be the isothermal and reversible process. Isothermal means that dt is 0, and delta T is 0. This means that for isothermal process, the change in inner energy of an ideal gas is 0. And remember, du equals Q plus W. This means that W equals minus Q. This is since here is a negative sign, and then here the negative sign drops for the expression of the work. It is the integral evaluated between V1 and V2. PdV. P would be again generally the external pressure, but since we have a reversible process, again P equals nRT over V. because it's reversible. This is pretty much a repetition of the process from the first slide, only with a bit more of explanation about how to calculate Q and W. However, now we can write an expression for Q. Q equals this integral here and this integral here as a... Okay, well, let's write it down again. Explicitly is integral in relative between V1 and V2, so the change in volume. So here we can substitute nRT divided by V dV equals nR and T are constant because we are dealing with an isothermal process. Here V1, V2, dV over, sorry, V, it is N, oh sorry, can N nR T, the logarithm of V2 over V1. So let's say if the inner energy does not change and let's say the system performs some work on its surrounding, then meaning that the work term is negative, then the heat term has to be positive to let's say keep the energy constant, and also also keep the temperature constant, because for the ideal gas the change in inner energy only depends on the change in temperature. Now we have covered I think all cases. Now the last thing was we wanted to cover the isothermal process. This is now also done. So all the, so to say, nomenclature has been covered in this video, and at the end of this video I would like to give an example for the first law of thermodynamics when dealing with an ideal gas, namely that the ring integral is 0. So here we have again our PV diagram. So let's start drawing. Let's say we start here at P1, E1 and T1. And when we have an isothermal and a reversible process, we go down. Oh, sorry. Of course, here it's volume and here it's pressure. Hope I didn't make this error somewhere else before. Here now, but however here final state would be P2, V2 and still T1, because this path here, path 1, would be isothermal and reversible. And the goal of this example is here that we have now two other sub-processes, and they end up at the same point here, and it's just let's say checking if with our constant so far we can with formulas write down that indeed the change in inner energy for both paths is 0, because here for isothermal reversible processes the change in total or inner energy is 0 because the temperature does not change. So first, to do this, let's draw some second curve. And the second curve should describe adiabatic and reversible process. So, and here we should end up at let's say P3, V2 and temperature 3. Why could I draw this curve like this? Therefore, let's consider for path 2 that we have a falling pressure, and this pressure depends on, let's say, V according to the axis, but also on the temperature, because for the adiabatic process the temperature is not constant. So let's write this, that general P for the adiabatic process is a function of the volume and the temperature, but the temperature again is a function of the volume, as we found out here. Let's look at this expression. Let's say I can interpret here T2 and V2 as a variable, and then I could express the temperature with the means of the volume variable and the initial volume. And since we are dealing with ideal gases, let's write this nRT over V. And we have found out that when the ideal gas is expanded in an adiabatic and reversible process, that always the temperature drops. So this means that, let's consider this here as a variable, T is always smaller than T1. And this means that P is always smaller than the pressure that is present during path 1. So P is always smaller than the pressure for path 1. And because this is the case, we can draw the curve like this. So the pressure here for the isothermal reversible process is always bigger than the pressure during an adiabatic reversible process, because the temperature here through the whole process is smaller than T1, and we can express this with the ideal gas law. And to be very precise, this holds for all V. So it holds for the whole interval as well between V2 and V1. And the final step would be that we have we go back, and to go back the third step needs to be isochoric. This means that delta V is 0, and for this path here then also the work is 0. Now let's calculate for path number 2 the work, and also Q, but Q we do not need to calculate because we are dealing with the adiabatic case here. Q2 is 0. This means that for process number 2 again, the change in inner energy for path 2, I just write it delta U2. Hopefully this does not lead to confusion. It's the work done during path 2, and this is again the integral evaluated between T1 and T3. Here I could have written T2 as well, but yeah, doesn't matter. Of CV dt. CV is again constant, doesn't depend on T, and therefore I can write this expression as 3/2 R ideal gas constant amount of substance T3 minus T1. and again here Q2 is 0, and for the isochoric process delta U3 equals Q3, the heat exchange during the third process. And one thing I forgot, I draw also arrows denoting in which direction we go in the diagram. And Q3 here is the integral evaluated between T3, T1, CV, dt. This equals 3/2 Rn T1 minus T3 equals minus 3/2 Rn T3 minus T1. And now finally, for proving our concept or showing that this terminology indeed is correct or innerly consistent, that we have to, let's say, address the change during process 2 and process 3, so change in inner energy when going first along path 2 and then along path 3. This equals delta U2 plus delta U3. In general, this equals Q2 plus W2 plus Q3 plus W3. So Q2 is 0. W2 we have found an expression for. It is 3/2 Rn T3 minus T1, and the expression for Q3 is here. It's minus 3/2 Rn T3 minus T1, which is essentially the same term as here. And finally, in the third step in the isochoric process, the work is 0. So W3 is 0 plus 0. And since these two expressions 0, they equal each other. Everything equals to 0, which we wanted to show. So indeed, for an ideal gas, a ring integral, or the first law of thermodynamics, holds that, or for this example, the first law of thermodynamics holds if they go again across the first path where the temperature is constant, the total energy of the ideal gas does not change. If you go a different path but end up at the same point here as for the first path, then also the change in the total energy is 0, which is in accordance with the first law of thermodynamics. So hope you enjoyed the video. Was kind of enjoyment for me to record the video again, and see you next time.